Hey kids, time for the chain rule in multivariable. So I do want you to remember a little bit about the chain rule from Calc 1. Remember where I reminded you of the composition of functions, for instance, where I had if f of x was equal to sine x and g of x was equal to x squared. If you were given the composition of f of g of x, which would be sine of x squared, and I wanted the derivative, you took the derivative of sine at x squared, but you had to remember to spit out the derivative of x squared. So the derivative of a composition is a product. And then after we practiced that, I talked about, what if I have a different variable in my second function in the composition? So what if I had some function in terms of x, but then chain this function, which is in terms of x, I have a new function x defined in terms of t. That the chain rule, I could think of the chain rule here as a product where C the chain, B the chain, right? Cancel out the dx's. Well, now suppose that you have right, and I can get the derivative of y with respect to t. Y wasn't defined in terms of x, but I want, because I have x also defined in terms of t, I now want y in terms of t, and I want the rate of change of y with respect to t. Now, what if I have a function that is defined in terms of two variables, but I also have that x is some variable in terms of t, and y is some other variable in terms of t. I'm sorry, some other function in terms of t, right? So here I still want a composition. What if I said f of g of t and h of t? And then further, I want the rate of change of the function f with respect to t. How is that going to work? Well, it's also shockingly going to be a product. But it's going to be a product, a sum of products. So notice that I define my function f has a domain of x's and y's. They're independent, and then I operate with some function and get up into the z-plane, right? This surface in z. Given, of course, that I have differentiability, however, x isn't just a point. X is a function in terms of time, and y is another function in terms of time. Then the rate of change of z with respect to time is a sum of products. Notice you still see the chain. Partial z, partial x times the derivative of x with respect to t. And partial z, partial y times the derivative of y with respect to t. So notice that you have two partials and two not partials. And you end up with the rate of change of z with respect to t. Now, sometimes in your book, you'll see the z replaced with this f. Oops, sorry. So the derivative with respect to t of the function f, which is in terms of x and y, can look like this, right? So all I did was replace the z's with f's. But still notice where you have partials and where you don't have partials. Also notice your chains in both places. So let's do an example. Suppose I had a function z in terms of x and y where it's x squared y minus y squared, but x is defined to be sine of t and y is defined to be e of t. And I want the rate of change of z with respect to t. So I have to take partial z partial x, and I do have to take partial z partial y, but each one of those has to be multiplied by d what? Right, x. dy. Yes, I know this is d and that's partial and that's del. That's okay. Right, so what do I have here? Partial z partial x is 2xy minus the derivative of the constant y squared. Partial x, I'm sorry, the derivative of x, right, in terms of just the one variable t, dx dt, is cosine t. Partial z with respect to y, times just dy dt. Now, think about when you were in Calc 1, there were times where you took the derivative of y with respect to x, and it was okay to have x and y stuff in the answer. So look at what I have. It is okay to have z and t's in my answer. Who can't I have? That's okay. I have what x and y are equal to. And just putting the e to the t at the end. What if I had asked you to evaluate this at t equals 0? At t equals 0, you're just plugging in 0 for t's, right? So sine of 0 is going to make that whole thing go away. Sine of 0, whoops, I wrote an x and I meant a t. That's a t, right? Sine of t, that 0 is going to go away there, and you're just going to be left with 2 times e to the 0, negative 2 times e to the 0 times e to the 0, which is negative 2. But notice I could have maybe saved I mean, it wasn't that big of a deal. But if I am asked to evaluate that derivative at a value, I don't have to plug in. I don't have to, go through the trouble of replacing the functions because I can evaluate x at 0 and I can evaluate y of 0. And I could have just plugged that in here, right? 2 times 0 would have made this whole thing go away, plus 0 squared, and I would have left with negative 2 times y, which would have been 1, times e to the 0, which also would have been 1, so I would have gotten negative 2. Speaking of avoiding replacing, I could have avoided the chain rule altogether with this problem, right? I could have just made z in terms of all t from the beginning before calculus, right? That would have been sine squared of t, replacing x with sine t, times y, minus y squared, e to the t squared would be e to the 2t, right? Now I'd have to, now when I wanted to just do dz dt, I'd have to do the product rule here, but that's not too bad, right? I would have gotten e to the t times sine squared t, right? Because sine squared t times the derivative of e to the t. plus e to the t times the derivative of sine squared, which would have been 2 sine to the first times the derivative of sine, minus the derivative of e to the 2t, two sine cosine e, 2 sine cosine e, sine squared times e, negative 2 e to the t times e to the t is negative 2 e to the 2t. Okay. But you're not always going to do that, right? Or want to do that because it's going to get a little bit more complicated. Before it gets more complicated, let's try another example together. Okay, you might want to pause the video and see if you can do this one yourself. But notice I asked for dz dt. X is defined only in terms of t. Y is defined only in terms of t. So I'm going to draw a little picture here. I'm going to say z is defined in terms of x and y, but x is defined only in terms of t, and y is defined only in terms of t. So look at what this tree diagram is telling me to do. Since I want dz dt, you're going to have a sum of derivatives. Take the partial z with respect to x, and take partial z with respect to y, as well as dy dt. Remember, since y and x are only defined in terms of one variable, I can say dx dt and not del x, del z, del x. So what do I have here? Partial z, partial x is going to be 2xy. And dx dt. Whoops, I'm sorry. I was going too fast there. 2xy plus I have something else, right? Now do dx dt. And dz dy times dy dt. Now, I am concerned because I've got too many variables. I'm not supposed to have an x and y's when I'm dealing with dz dt. However, they asked me when t is equal to 0, so I don't have to go through the trouble, right, of replacing. I just can say, well, what is x when t is equal to 0? And what is y when t is equal to 0? And now I can go down here and replace. 2 times 0, right, that term's going to go away. So I'm going to have 3 times cosine. Cosine of 0 is 1 times 2, right? Plus 0, 0, sine of 0, 6. forgot to check that out. All right, now, what if, though, I had a function z that is in terms of two variables, but what if x itself is a function in terms of two other variables? And the same with y. I want you to think of this as that tree, right? I want you to think of z is in terms of x and y. X is in terms of s and t. Y is in terms of s and t. And now I can't get one full derivative, but I can ask you for partial z, partial s, and I can ask you for partial z, partial t. And look at what your tree is telling you to do. Figure out how I land at the s's and add them together. So how do I get down to s? I start at z, and then I need to do so. And look how I still have the C the chain, B the chain situation, right? How else do I get to S? I need to go down this branch, partial Z, partial Y, and then come down here to get to the S. How would I get partial T? Follow the tree. I have to go down the same branch here, but what am I multiplying by? And start the same way. Times and again, I can see the chain, be the chain, and notice that I have two partials added together. I kind of think of that as giving me my whole partial, right? So let's do an example like that. So here's those two written out without the tree. If I want partial z, partial s, or if I want partial z, partial t, or you could think of that with your tree. Look at my pretty tree. There's my z. What do I ask you for? If I'm asking you for partial z, partial s, follow the branches of the tree everywhere to get to an s, add it together. If I ask you for partial z, partial t, follow the branches to get me to the t's, add them together. Now, we can keep going and going if you want. Look at this. Oh, my Lanta. right? Look at this. Here's my W. If I want my partial W, partial S, notice that I've got all S's down here. Partial T, all T's. I mean, I have my X, Y, and Z. There's my S, T, and R. Here's what that all looks like as a tree. Right? If I start with W and I ask you for partial W, partial S, follow all the branches that get me to an S. And add all three of them together. If I wanted one, two, three. One, two, three. Let's do an example like that. Now, notice since we're not given any values, it didn't say when something is equal to 0 or whatever, I have to remember that I put U and V back in my final answer. Right? So how many things are going on here? So I have to first, how big is my tree? Right? So I have W is in terms of X, Y, and Z. X is in terms of U and V. Y is in terms of U and V. Z is in terms of U and V. They want dW, du. So let's use the tree and figure out how do I get from W to a U. 1, 2, and 3. So and right? C the chain, B the chain. So partial W, partial X. Partial X, partial U. Partial W, partial Y. Partial Y, partial U. And partial W, partial Z. Partial Z, partial Z, partial U. Don't forget that you need to replace the V's and the U's. I'm sorry, the any X's. I don't know why I boxed my V and my V. My V and my U can stay, just my X. My X is, so that's 2 times U minus V. Okay. I will leave you to do partial W, partial V on your own. Let me do one more example with you because I skipped doing one with 2 and with having to replace. So what if Z was equal to 2xy and X was equal to U squared plus V squared, and Y was equal to U divided by V. Partial V, partial U is what I want. So my tree, Z, so I need partial Z, partial X times partial X, partial U, and right? So partial Z, partial X is 2x, partial X, partial U. I'm sorry, I was looking up here again. Partial Z, partial X is 2y, but partial X, partial U is 2u. Partial Z, partial Y is 2x. Partial Y, partial U is just 1 over V, right? But I don't, again, have, this time I must replace. So who do you have to replace? So what do I have here? 4u squared. And here's 2u squared, so that's 6u squared. And then 2v squared. And that's all on top of v. All right. So there we go with the first day of the chain rule. We'll continue with this in the next video.